So here we are exploring descriptions of the solutions to a linear system. So solving a linear system to its row-reduced echelon form provides us with an explicit description of the system's solution. Now there's two cases that we need to consider for consistent systems. And that first case is our favorite case, the case where we have one unique solution. Right, we're always kind of hoping that a matrix reduces to have one unique solution because it's the most beautiful. In this case, we would say that the coefficient matrix of our system is actually the identity matrix. So the coefficient matrix is equal to the identity matrix. And the identity matrix, we'll make a little love note here to ourselves. We denote this as I sub n. And that n is because your identity matrix is an n by n square matrix. It must be square. So IN is our identity matrix, that n by n square matrix, with ones along the main diagonal and zeros everywhere else. So if a system has one unique solution, the coefficient matrix is equal to the identity matrix. And we'll be more careful here. Instead of using an equal symbol, we should use the equivalent symbol. Now, if your system has one unique solution, we say that each variable in the solution vector x is a basic variable. So each entry in the solution vector x, and because the identity is in n dimensions, the solution vector must be in Rn. So each entry in the solution vector x is called a basic variable. So this means it has a solution, has a distinct solution. So let's think about what this would look like in an illustration or in an example. And give ourselves a little bit more room. So for example, a system that's going to have one unique solution is going to look as follows. So we have the identity matrix is our coefficient matrix, so 1, 0, 0. We'll do it in R3, 0, 1, 0, 0, 0, 1. And so again, this coefficient matrix here is your identity matrix in 3 dimensions. So this is our identity matrix, and we would denote this as I sub 3. And that's because it is in 3 dimensions. So notice those pivot positions along the main diagonal. They're all 1s, and everything else is 0. And now, again, this has one unique solution. So we're going to be able to find a specific numerical value for each of our basic variables. So what is this telling us here? We should include, of course, this is such that DO and G are scalars. Like there are constant values. So when you're able to reduce a matrix to its row-reduced echelon form as we have here, and we attain the identity matrix, this is telling us the following. This tells us that x sub 1 is D. This tells us that x sub 2 is 0, or O, and that x sub 3 is G. This tells us the solution for each of the entries in vector x. Now we can take this one step further and provide a parametric description for the general solution. So we can say that therefore the parametric description of the general solution is defined as follows. So when we talk about a parametric description, we want it in our vector form. So vector x is a vector in R3, x sub 1, x sub 2, x sub 3, such that we now know x sub 1 is equal to D, that x sub 2 is equal to O, and that x sub 3 is equal to G, such that D, O, and G are scalars. Now this is the case, the beautiful case, where we have one unique solution. What about if we have infinitely many solutions? Let's take a peek.